Okay. I'm Sean Parent. As mentioned, I'm a senior principal scientist. I'm currently running Adobe's software technology lab. Until relatively recently, I've been working with the Photoshop and Lightroom teams. So I worked on Photoshop Mobile and Photoshop Web, which recently shipped, as well as Lightroom Mobile and Lightroom Web. So I've got a fair amount of product experience and trying to take large products and make them run well on mobile devices and on inside of WASM on the web. So I do want to mention Adobe is hiring. So there's a link here. We have many C++ positions open and just many software development positions, including web development positions. So I encourage you to check out the link. You can also go to careers.adobe.com for a complete list of all of our open positions. So I'm going to give you the answers to my talk before we get too far into it, which is where all of our cycles have gone is into sand in the gears. And there's a lot of sand in the gears. Unfortunately, the problem is not one thing, but rather it's the cumulative effect of many factors. I will discuss some of what I see as the most critical of those factors, but there is more sand. Notably, I'm not going to discuss I/O at length, but we'll touch on it in some other contexts. So I'm going to talk some about memory latency and the problems that memory latency causes and why it's there. Problems with synchronization. Expanded requirements. This is the fact that we are actually asking our software to do more these days. And problems with our current programming models. So let's start with memory latency. This is a graph from Hennessy and Patterson's computer architecture book. I wasn't able to find a updated version of this graph. You can see it stops in 2010, so it's about 12 years behind. But if you project out looking at, say, DDR5 memory speed, it's about 16x what you see here in 2010 for memory speed, which seems like it would move that line a lot, but this is a logarithmic scale. So it actually is tracking pretty much on target on the same linear progression for memory performance. And the processors, as we've kind of tapered off on Moore's law, the processor performance has continued to taper off and is now pretty much tracking memory speed. And so our memory gap remains just about fixed between the two. So if we look at that processor memory gap, what that's led to is a very deep memory hierarchy, where we have register operations that execute in typically one or less cycles. An L1 read, you're looking at on the order of 8 to 10 cycles. An L2 read, you're looking at something closer to 20 to 30 cycles. L3 read, you're in the range of 50 cycles. If you have to hit main memory, you're looking at somewhere between about 150 to 175 cycles. And because we're trying to maximize total bandwidth on the machine, we see an increasing amount of hardware shipping with NUMA architectures. And so here you have separate memory buses for a group of cores. And so within a new architecture, you pay an additional penalty if you have to cross buses and fetch something from another core's bus. Just for an L3 read, which is L3s are typically tightly integrated across the new architecture, but even so, you're looking at a bigger hit than main memory. And if you're looking at cross socket to main memory, you're looking at somewhere between 300 and 500 cycles. So the net effect of this is that you have to start thinking about memory as if it were a tape drive. Memory and caches tend to work by read ahead, which means they're trying to predict your cache access patterns and prefetching data ahead of you within the cache. And if you have to back up or if you hit a miss, it's the equivalent of an old tape drive. That tape drive has to rewind or seek ahead, and you're going to pay a significant performance. So let's talk a little bit about what happens with synchronization. So this is a chart from the IT Hair website. It's an infographic plotting out the relative performance of common low-level operations, and it's presented on a logarithmic scale. I typically recommend every engineer just familiarize themselves with this graph because there's a lot of useful information on here, including all of the memory information that I just presented on the previous slide. But I don't think people consider specifically the cost of threading and synchronization operations. So let's take a look here. If you see, the first thing to notice is that atomic operations fall just about in the middle of this graph, where you're looking at 15 to 30 cycles for a simple atomic operation. It's easy to miss under this, but kernel calls are 1,000 to 1,500 cycles on a modern OS. A mutex under contention, not under contention, hopefully it turns into an atomic operation, but a mutex under contention is going to turn into a kernel call. And so that's going to cost you this 1,000 to 1,500 cycles. And way down here at the bottom of the graph, clocking in between 10,000 and a full million cycles is the cost of a full context switch if the processor is under contention. So ideally what we want on our machine is to have one thread per core and have all of those threads running flat out, none of them having to wait. Now, the problem gets a little worse if we look at Amdahl's law and what the actual cost of synchronization is. So if you look online, you'll typically see Amdahl's law plotted out on a logarithmic scale. And that's not, I don't think, particularly meaningful because we're rarely dealing with devices that have thousands or tens of thousands of cores. So this is on a linear scale, just plotted out to 16 cores, which covers the vast majority of desktop machines these days. So each line here represents the cost of having just 10% synchronization within your application. So if we had no synchronization and we added more cores, our performance would scale linearly. But if we only have 10% of synchronization and we're all the way out at 16 cores, we're looking at just a little more than a 6x speed up. This is one reason why CPU manufacturers don't just put hundreds of cores on your device. You would get very little benefit of them. In fact, the bulk of consumer machines these days have between 4 and 8 physical cores. And you can see why those lines ramp off at a very steep rate And unless we have software that's trivially parallelizable and gets up above 90% parallelized, you're just not going to see much performance benefit beyond 8 cores. Ivica talked a bit about chatting components using mutexes and contention. I actually see a lot of that in the software I work on, and you can see in this graph why that ends up just killing your performance. And the next piece I wanted to touch on is expanded software requirements. I took a snapshot of my Windows box. I also took a similar snapshot on my Mac box, and both were about the same. My machine idling with the usual set of applications that you would find running, a browser, Slack, mail. I've got an iTunes server running on this machine. You're looking at somewhere between 5 and about 15% CPU utilization, and I typically see 30 to 40% memory utilization. This is on a 32 gigabyte machine, so it's not a particularly a low-end machine or limited in RAM. So that has an impact. I was very surprised when I took the snapshot that my contact list is using 5.6% of my GPU, and it's using a video decode unit. I have no idea why that's happening, but apparently my address book needs to do video decoding. So when I look at my M1 MacBook Pro numbers, they look surprisingly similar to what you would see on a Windows box. So as I mentioned, my machine, my Windows box, my home machine is Hades Canyon Nook. So it's a few years old, but it still outperforms kind of the sweet spot for desktop machines in the consumer market these days. So if you look, again, this is just running typical apps and the machine is idle. You see there's over 5,000 threads spun up. Now, most of those threads are going to be parked, and so my machine is not necessarily overcommitted, but this still has a performance impact because typically the stack for a thread is wired memory, meaning it's not eligible for being paged out by the VM system, and so that's consuming my physical RAM and making less physical RAM available for other applications that are running. You can also see that there are over 300, almost 400 processes running. Many of those are parked, but many of them are on timers, and so they will wake up and thrash caches and have a significant impact on performance. If you look here at the cache sizes on this device, you get a sense for just how small our CPU caches are. Our L1 cache is only 256K bytes. Our L2 cache is a megabyte. L3 cache is 8 megabytes. As you'll see in a moment, 8 megabytes of memory these days is not even enough memory to hold the memory for a common display. Now, the other thing to note here is the difference between physical cores and logical cores. The reason why we have this difference, logical processors are referred to hyperthreading, and this is a combination of a hardware and software approach. There's kernel level support for this as well as hardware support for this. And basically what's going on here is you have 4 physical cores, but because those cores are going to be spent some time waiting, typically on main memory, the hardware and software is able to invoke a context switch and execute another thread on the same core during those waits without waiting for a regular interrupt-driven preemption or waiting for a mutex to trigger a preemption. Logical processors typically give you about a 15 to 20% performance boost over just the number of physical cores, just by being able to fill in some of those gaps. But they also come at a cost because there are not additional caches for those virtual processors. And so every time you have a wait on main memory and you're switching to another core, that core can be pulling things from L3 cache into L1 cache and polluting your L1 cache for when you return back to the previous thread. So we talked some, as we're talking about putting the additional requirements on our devices here, besides just running background tasks and processes and having more threads going on within our applications, our screen dimensions actually play a significant role, at least with desktop apps and with operating systems in their performance. So if you look here, this is the progression for the amount of memory in megabytes needed to render out a single frame. So this is not actually display memory, which can sometimes be a more compact form, especially when you get into HDR, where HDR is usually represented in hardware as being 10 bits per component. But if you're manipulating it, we don't typically have 10-bit data types, so you're working with 16-bit components, either on your GPU or your CPU. So if we look here, when I first started professional development, it was on an original Macintosh, and that was looking at 0.02 megabytes for a 1-bit 512 by 384 display. Now, the displays that I have in my office are 4K displays. So those you're looking at 24 megabytes, which I mentioned. That's significantly more memory than you even have in the L3 cache. In fact, then once you move beyond 1080p, you're blowing out of your typical L3 cache. So Apple's Studio Display is a 5K HDR display. So that's putting you all the way up at over 88 megabytes to render out a single frame on there. Now this chart is not looking at display over time, but that 5K display is 120 hertz as opposed to 60 hertz. So if you wanted to compare it down to bytes over time, you would double that number one more time. There are a number of 8K displays, 8K HDR displays now on the market. Dell makes a very nice one. An 8K HDR display, you're looking at 200 megabytes of data to drive it. The other thing that this doesn't encompass is many users will have more than one display. It's not uncommon to see rigs with 2 or 3 4K displays connected to them. Now, the interesting thing with displays is I don't think that this chart's going to keep going up forever. We are pushing the limits of human perception. In fact, my aging eyesight here, I have a very difficult time personally telling the difference between 720p video and 1080p video. I certainly cannot tell the difference with video between 1080p and 4K. For stills and text, I'm fine at 4K. I can see a minor difference with 4K HDR. But that's about it for me. I really can't see at a 5K HDR or 8K HDR. In fact, there's a a relatively small percentage of the population for which an 8K HDR display would make any difference at all. So at least as long as we're sticking with 2D displays, I think we're running out of tech. Of course, if we're looking at VR displays, then the bandwidth gets a bit more complicated. And if we're looking at light field displays, you're looking at 10 to 20x these numbers. And that brings us to programming models. So we have a lot of sand in our current programming models. Our languages and usage of this language bias towards reference semantics, which means we have lots of heap allocated objects, which means we have lots of cache misses and memory latency. Each of those is costing us 200 to 500 cycles. To manage the lifetime of those objects, if you're using something like a shared pointer, you have atomic ops. If you have a garbage collector, you're still paying a penalty. The penalty is just bucketed and amortized, but it works out to be about 30 to 60 cycles. Indirection and virtualization, we pay a penalty on that every time we follow an indirect pointer or make a virtual function call. We're paying an additional 10 to 20 cycles over just a straight call. Thread context switches, as I mentioned, are incredibly expensive, 10,000 to 1,000,000 cycles. The dispatch cost to dispatch a task onto a thread is typically in the 500 to 600 cycle range. Our languages are biased around structuring data in arrays of structures. What this means is, let's say I've got a struct or a class. It's got a number of members in it, and I want to store that in an array, or say a vector, or any kind of dynamic array. The way that that's going to be structured is just a sequence of those structures into the array. The problem with that is that's a very poor way to structure data if you want to make use of SIMD instructions and parallelization, and so it usually defeats almost all vectorization optimizations out of the chute. And so for every time we're accessing this structure, we're paying an additional 8 to 32 cycles. Raw loops. This is the notion of our languages making it too easy to just drop in a while loop or a for loop. This is opposed to having an algorithm that can be parallelized either with SIMD instructions or onto a GPU. We lose a lot of potential performance to people hand coding loops. It can easily be on the order of 100x. And then the other thing that we are paying for in modern hardware is JIT compilation and garbage collection. We're doing a lot with JavaScript and Python these days, and even Java. And best case, very conservatively, you're looking at about a 10x performance hit. So why have our programming languages evolved with these inefficiencies? Well, some of them are historical, right? If you look over time, certainly when I started coding, there wasn't this performance gap between memory and processing. It was basically one cycle to get to mean RAM, and we had no cache hierarchy. The result of that is we tended to design things around, and design languages around heap allocated objects, because there was effectively no cost on that compared to keeping it local, or at least very minimal cost. And made heavy use of node-based data structures, things like std map, even std hash map is a node-based data structure, std list, which you should probably never ever use these days. All of those had a much reduced relative cost. So there's also the reality that languages have been optimized for ease of development, time to market, and time to market concerns versus performance concerns. I think now we are, and have been for the last several years, have been switching gears where we are entering a realm where the driving costs on a lot of code that's getting deployed is actually the energy costs, and that's tightly related to the actual performance cost of that hardware. The web and security have imposed additional costs. There's a cost of sandboxing and mitigating side channel attacks. If you followed things like Spectre attacks, which is a side channel attack that's attacking speculative execution that has been built into most processors. Speculative execution is a way to try to also suck out some of those memory bandwidth delays. You can execute code down multiple paths on a branch before you even get there, and then just take the results of the route actually taken and discard the results of the routes that are not taken. The problem is through speculative execution, you can determine what values are actually stored in memory, even if they're memory that's not accessible directly from your process. So it's been demonstrated that you can write side channel attacks in JavaScript and just read out kernel memory or memory from other applications from within JavaScript using side channels. So the other thing that I think developers don't think about a lot is how much GPUs and increasingly ML units change the performance landscape on desktops. This is an old chart now. It's about a decade old, originally put together by Russell Williams on the Photoshop team. But at the time, he was looking at fairly high-end hardware. Same ratios apply today. If anything, they've gotten a little bit worse as GPUs have outstripped CPUs just by a bit in their performance scaling. But if you look at a typical processor, the bulk of the performance is or a typical desktop machine or laptop, the bulk of the performance is actually trapped inside the GPU. So next comes the vectorization unit, which is down here. Auto vectorization will help improve performance of your C++ code, but because of how we lay out data, not nearly by as much as we would like, which leaves you mostly using intrinsics to try to unlock vectorization. Down in this little slice is what you get if you can correctly utilize the multiple cores on your machine. This was an 8-core device that we're looking at here. And that's assuming you're trying to circumvent Amdahl's law as much as possible and getting good scaling. And this little strip down at the bottom, which is 0.25%, is the performance, relative performance in the hardware of just a single-threaded, no vectorization code running on your CPU. Right? So you really have to think of the CPU as being the orchestrator that's figuring out how to feed your SIMD units and your GPU to unlock performance. So compared to this chart, today's higher end GPUs capable of about 6x the performance of what this device was. So you're looking at about 20 teraflops, which is a tremendous amount of GPU compute power. But the architectures compared to here have become more complex. On the CPUs now, we're trying to deal with performance and efficiency cores. We have thermal considerations, which we didn't have even just a few years ago. We have unified and NUMA memory architectures, and each vendor in the space is trying to find a way to differentiate their products. So it wasn't that long ago where OpenGL and OpenCL were considered the way to write portable code to access GPUs. They are now both effectively dead. We have CUDA on NVIDIA, which is the closest thing that we have to a generalized compute model for GPUs. CUDA has been working towards executing just straight C++, standard C++ directly on the GPU. Apple has Metal. There's an open standard called Vulkan, which is mostly just Linux, although it does have some play on Windows. Unfortunately, no play on Mac or the web. And then we have Web GPU to access the GPU within the browser. And we have alternative languages like Halide, which can access GPU and SIMD. It's a dedicated language for doing image processing and for doing ML. And then on top of this, we have to add ML units for machine learning units in Apple's higher end M1 based machines, like an Apple Studio. You're looking at another 20 teraflops of compute power inside the MLU. So what does the available computing power on high-end machines look like? As we said here, this machine that we were looking at was relatively inexpensive, and it scales out. So I mentioned before, straight line C++ code, you're down at 0.25%. That's maybe down to about 0.2%, if not a little bit lower, if you looked at new hardware. So how do we start digging out and get the sand out of these gears? Well, I think hardware manufacturers now, as clock rates have stopped scaling and as they've been bumping hard into Amdahl's law and trying to push more cores on the devices, we're seeing significant shifts into unified and shared memory models. So instead of having separate memory on the GPU, we're seeing a lot more go into shared memory models where both the CPU and GPU are sharing the same memory, which reduces the latency between transferring computation between the two. And Apple has already moved to a unified memory model. This is where the memory is not just shared between GPU and CPU cores, but it's directly connected to the processor. So it's unified on the same die. So you have lower latency and faster access. And Intel is moving in the same direction, and I expect AMD is going to follow suit as well. So I think we need OS changes. OSs right now don't do a great job managing cores across processes. What I mean by that is if you have two processes running and both of them are spinning up thread pools and trying to maximally utilize the machine, they're both just thrashing the caches of each other. We really need operating systems that can do a better job of, of, of managing those cores. We're seeing more of that come into play, especially as we get more heterogeneous core architectures. And the OS is both trying to manage thermal throttling on the machine and efficiency by migrating tasks or migrating threads from a high performance core to an efficient core. We really need the OS to start providing hints for around thermal memory, heterogeneous cores, and cache utilization. Frankly, as a developer, when it comes to these issues, you're running mostly blind, right? It's very difficult to get information about how much you can saturate cores before the operating system is going to come and throttle you because you're going to get thermal issues. So the other place where I think OSS could provide some help is with coordinated asynchronous, especially direct memory access based I/O. We're seeing more and more hardware that has DMA for SSDs. Initially, that was just to the main CPU, but now we're also seeing, if you look at like PlayStation 5 and some of the modern PCs, you're seeing DMA access for I/O so that GPUs can read memory directly without going through the CPU and without consuming additional processor cores. But we really need better OS support to coordinate that. This is true around network I/O as well. It is very difficult for a single process to have enough information to saturate I/O without overcommitting the I/O and starting other tasks. So I think we need a lot of programming language changes to change the programming model. We need to be moving more towards what I refer to as performance by definition, not by optimization. We currently rely too much on trying to let the optimizers pick up the slack. But there's a lot that needs to be changed around data layouts and that directly impact how programmers solve a particular problem. So one of the first things that I want to see is languages evolve more around mutable value semantics. If you want a reference to this, go look at Valang. The root of most problems, both around safety and contention, and many of the performance problems around memory access, is around shared mutable access to data. But it isn't enough to eliminate mutability, which is what functional programming tries to do, because mutation is required for efficiency. And so instead, we have to stop sharing the mutable data. The Rust language is another language which is going this direction. Unfortunately, the Rust language is very reference semantic heavy, which means you're newing objects, which tends to imply heap allocation, and then hoping that your optimizer can come along and eliminate those heap allocations. But those optimizations are not guaranteed, and because of the programming model, actually rarely kick in. So you have some win and some loss, but the Rust languages emphasis has been more around safety than kind of absolute low-level performance. So we need to be moving towards a structured task concurrency model. I think raw threads should strictly be banned. The best work these days in this space is from Eric Niebler, who was doing this work at Facebook. Now he's doing it at NVIDIA. There are still some significant outstanding problems in this space. We don't have a good solution for grain size control. Grain size within a tasking system is a measure of the amount of work that a given task is going to do before you allow that task to complete and schedule another task on the same core. The problem is that unless you have kind of a trivially parallelizable problem, you're doing data parallelization, you don't have local information about the grain size. If I call some operation and it's doing something asynchronously, and I want to effectively attach a continuation to that operation, I don't know if I should break the grain or not. I think to do grain size optimizations, we're going to have to get into a profile guided optimization scenario. And that means that we're going to need higher level semantics around what grains are, so that an optimizer can make those decisions. So another area where we don't have good answers right now is around having explicit data dependencies for thread affinity. If I have two tasks which are sharing data, they might be split into two tasks instead of just one large task, because I'm trying to optimize for latency, not just throughput. I want the ability to tell my task scheduler that these two tasks are sharing the same data, so it can try to schedule them on the same thread, hopefully by implication the same core, so that I don't pay the equivalent of a context switch and thrash my caches between tasks. So GPU and SIMD execution models. Again, Eric Niebler's work out of NVIDIA, along with Bryce Adelstein. They're doing some good work in this area. They're not taking it as far as I would like it to go. If you look at something like Halide Lang, which I mentioned before, this is a dedicated language for doing image processing and ML work. Or if you look at shader languages on a GPU, the basic idea is that you're able to have an algorithm into which you can plug in a computation kernel, and because the algorithm provides the structure for the data access and the scheduling of that kernel, the kernel can be optimized for executing either under SIMD or in parallel on the GPU. So the final piece here is, as I mentioned before, our languages are biased around structures of arrays. To unlock SIMD performance and GPU performance, you actually want to invert that. You want a structure of, I'm sorry, we currently have arrays of structures. What you want is a structure of arrays. And you want this to be kind of deep and transitive. So, if I've got a class that contains members, and I create an array of those, I want each of the members hacked out into separate arrays so that I can write SIMD optimizations to go over that. An extension of this is arrays of structures of arrays. This is taking those structures of arrays and bucketing them to cache lines, because if you have a structure of arrays, eventually to access a single object, you're going to be going across multiple cache lines because as your array grows larger, the difference between individual members will grow. So arrays of structures of arrays is a data format that basically buckets those things along cache lines. There are a couple of good libraries out there that do this. They're all quite complicated to use and quite difficult to use correctly. But this is an area where I could have a construct within a language where I just, instead of saying I want, you know, a vector of employees, I could say that I wanted a vector of employees, but structure it as an array of structure of arrays, and then apply through my algorithm and execution abstractions operations on that would be SIMD optimized and parallelized. So that's the end of this talk. I see I've got one question already here. A little credits to the artist for my slides. Here we are. So the first question that I have is, how do you measure the percentage of synchronization in code? That's a challenge. This goes back to Ivika's talk. vTune, if you're running on an Intel box, is quite useful. Apple has similar tools for looking at the processor counts. Typically what you're looking at is most modern processors, both Intel and ARM, have a set of counters that they keep internally. So you want a profiling tool that will let you look at those counters so you can see when a core is stalled and flagged. But you know, these things are places where our tools, I think, even with vTune, are relatively primitive, and typically what you're looking at is looking at bottlenecks within your code and tuning those. And I think that's unfortunate because, as I said, a lot of the issues is just sand in the gear, which means it's very, very distributed. So a lot of times what you can do is just drill in on a very small section of code and try to look at the performance of it. And then try to extrapolate the lessons you learn in tuning that into the larger body of code. So the next question here. It seems to me that the future lies, this is from Flores, or Bob Flores, I'm guessing. Flores Bob. It seems to me the future lies in some sort of combination of generic algorithms, Stepanov style, data-oriented design, and C++ zero-cost exceptions. Would I agree? Yes, I would agree. You know, I think that's a fairly reasonable way of looking at it. You know, when I'm writing things like computations, I actually don't want to be writing them in terms of you know, integers or floating point values. I want to be writing them in terms of something like a normalized 8-bit value as a generic entity, and have an algorithm be able to plug that in using you know, SIMD or GPU optimizations to plug in the actual data types. So yes, I definitely think that there is a strong role for that. I think the STL, kind of as it is should get more use. You know, I think people here know I'm a huge proponent of it. There's a lot of benefits of it. I think under modern hardware, though, it really needs a relook. There are some very interesting algorithms out there. I was just reading a paper recently on on how to improve binary search performance by basically restructuring sorted data into an in-place tree, and that can provide several times performance speed up by improving cache locality for binary searches. And so I think there's a lot of interesting work that's been done like that isn't well reflected into the generic space. I think the idea of C++ as zero cost abstractions is good. I think unfortunately C++ breaks down in a lot of those areas, or just historically kind of made poor decisions. My common example is it's very difficult in C++ to see when doing an assignment is actually going to trigger a copy versus invoking RVO and understanding the rules of when RVO is guaranteed to come into play and when it's not is a challenge, typically even for a seasoned developer. And the result of that is that just something as simple as doing an assignment is not a zero cost abstraction. It's a potential performance cost, and it's not necessarily visible in the code, and it's hit or miss as to whether or not a particular compiler will optimize out a data copy if it's not guaranteed within the standard to be eliminated. So I would like to see things like have an explicit copy model in C++, which you can do today pretty easily by declaring your own copy constructors to be explicit. The problem is it doesn't help you with all the standard types. So do I have any recommendations for resources to learn about all the things you've mentioned? Boy, that's a good question. I think Hennessy and Patterson's computer architecture book is probably still the best place to start if you have no understanding of this. If you're just looking at kind of get an idea of some of the superficial ideas, I think the IT Here website, just search for IT Here cost of operations. That will give you a pretty good overview as far as Amdahl's law, and there's a set of related laws. Just do a search on Wikipedia. You can get a good overview of those. So those are the places I would start.
One more question for Sean. You started the talk with memory latency and the CPU memory gap. How do you see that changing with new technologies like CXL, pooled memories, near and far memory? Do you see this making the problem worse, or do you see it helping in the long run?
I think it's a challenge. I think to the extent that hardware manufacturers have just been able to speed up straight memory access, that's beneficial, although we haven't seen anything that's that bends that curve in the logarithmic space that actually starts to close the gap. But things like DDR5 memory and things of that nature certainly help. Most of the more exotic things all fall into some form of a new architecture where you have memory local to a given computation, and there are, I think, potentially huge benefits to that. You're even looking in the ML space Samsung is looking at putting processors in RAM, right? So you can do some amount of computation directly locally in RAM. And so there are certainly direct applications for that. I think the biggest challenge there is is what's the programming model? Programming to optimize for a NUMA machine is nearly impossible. We just don't have the right constructs and the right control to do it, which means you're relying on the OS to make some amount of speculative choices for you, and it's hit or miss. And a problem with that is you have no visibility to that within your program. And as we've mentioned, profiling those things is very difficult. And so you can have one piece of code that looks nearly identical to another piece of code, and one will run very fast, and the other one will run very slow, because the slow one happens that every hit to a data structure is cross memory buses, and that will just kill you. So these things are just very difficult, and we don't have the right programming models these days to deal with those problems.
I have one more question. So given that Adobe is one of the leaders in graphics processing space, and you have so much experience with designing generic algorithms that are fairly well suited for array programming, I wonder if you have explored using array programming paradigm, like in languages like APL or Julia, to apply it in at Adobe in some context.
Certainly, we've explored some of the ideas, and I think when I talked about structures of arrays versus arrays of structures, that touches on array-based languages. Array-based languages, you just tend to not use structures, you just use arrays, and so things will naturally SIMD optimize, and we certainly do some amount of that by hand. So I think there's some benefit in getting array language constructs to be more first-class citizens in our other languages. I would like to see more borrowing from that. But most of our efforts, related efforts in this space, I would say, have been around halide, which is where we're getting the most use for kind of optimizing of low-level code, and that doesn't look like an array language at all. I mean, it looks it looks much more like a GPU shader language, right? You kind of have a C++ code that you're writing a computation kernel, and then you're describing how you want that computation kernel scheduled across a set of data. So most of our work has been in that area and not in kind of the array language space. One of the complaints I frequently have with array languages is they also fall into this trap of sometimes you can write very inefficient solutions, which are very short and very terse and very beautiful. So it's also very easy in an array language to kind of hide the computational cost of the operations you're doing.
Especially in APL.
Yes. That's true in APL.
Well, thank you so much, Sean. Really appreciate the talk. I've learned a lot.